Hello, this is part A of the Chapter 8 lesson. This chapter is titled Power and Sample Size Determination. There are a lot of concepts and definitions and ideas in this chapter, and some of them are rather complex. In this lesson, we're going to try to simplify things down as much as we can and focus on the most important ideas. In part A, we're going to talk about confidence intervals, and then subsequent parts we're going to talk about hypothesis testing. And so one note here for this lesson, we're going to be using the Excel workbook chapter 8. So sample size. The first step in any statistical study, regardless of what type of study it is to determine the necessary sample size. We need to figure out just how many people do we need to survey. Is 15 enough? Do I need 50? Do I need 500? Do I need 5,000? Just what it is, just what do I need? Well, there's many factors to consider. There's financial. If we don't have a lot of money to spend, then we're not going to be able to have a very large sample size probably. Logistical, just how possible is it to get the data that I need? How much work is it going to be? Statistical. What does our statistics say about what our sample size is? And then another idea is attrition. A study could take the length of many years, and you may have some people who start the study but who can't finish it for whatever reason, and so you've got to take that into account. Now, in this lesson, we're going to focus on mainly statistical ideas and statistical considerations, and we'll briefly take into account attrition. Financial and logistic issues, those are beyond the scope of this class. So far we've talked about basically two ways of analyzing data. We have confidence intervals and then hypothesis testing. To do a confidence interval, we start off by choosing a confidence level, which is typically 95%, and then we go out and we collect our data and we calculate a margin of error, and then we use that margin of error to get a range of possible values for the parameter. What we're going to talk about here in this lesson is what does the confidence level mean? What does that number 95% mean? And then we're going to talk about what affects the margin of error. How does the confidence level affect the margin of error, and what else affects it? And then what does the size of that margin of error tell me about the range of possible values and how that range is important? The second way of analyzing data is hypothesis testing. In hypothesis testing, we start off by selecting a significance level alpha, which was typically 0.05, and then we compared our p-value to that. And then related to this significance level is an idea called power, which the book has talked about, but we haven't really mentioned it in any of our lessons. Here in this chapter, we're going to talk about what does that significance level mean in hypothesis testing, and what is power, why is that important, what does it mean, and what type of things affect the power, and how that can help determine our sample size. So let's start off by looking at example 6.1 from the book. Now this is obviously from chapter 6, but we're going to use this to illustrate some ideas. Suppose that we want to know the mean systolic blood pressure of all people, and let's call that number mu. Well, in order to find the exact value of mu, I'd have to go out and get information from every single person in the United States, I guess. Take their blood pressures, add them up, divide by the number of people, and that would give me the exact value of mu. Well, that's obviously impossible to do. So we go out and we get a sample of 3,539 people. We take the blood pressure of each. We calculate a mean blood pressure of 127.3 and get a standard deviation of 19. And so let's use this information to calculate a 95% confidence interval estimate of mu. And now this is what we did in chapter 6 when we talked about confidence intervals. And so to perform this calculation, we could use the workbook chapter 6, but I've actually put this worksheet in the workbook chapter 8. So if you go to that workbook and the worksheet mean, we can enter our necessary information here, our 95% confidence level, our sample size, sample mean, sample standard deviation, And and then it calculates the margin of error and gives us this confidence interval estimate. So we would interpret this interval by saying that we're 95% confident that mu is somewhere in between these two numbers, 126.6 and 127.9. Okay. Now let's look at changing some things here. And so we're going to look at first changing the confidence level. How does the confidence level affect the margin of error and our confidence interval? So here at the first is our original calculations with a 95% confidence level. Here's our margin of error, and here's our confidence interval. Now let's suppose that we try to use an 80% confidence level. And our summary statistics here don't change at all. We just have an 80% confidence level. Now look at what that does to the margin of error. It went from 0.6 down to 0.4. So we have a smaller margin of error. Now look at what that does to the confidence interval. The lower limit went from 126.6 up to 126.9 almost. So the lower limit got bigger. Look at what happens to the upper limit. It went from 127.9 down to 127.7. So the upper limit got smaller. So that means that our lower limit and upper limit got closer together. So that gives us a narrower range of values for our possible values of mu. So we would interpret this by saying that we're 80% confident that mu is somewhere between 126.9 and 127.7. So smaller confidence level gives us a smaller margin of error and a narrower confidence interval. Now let's increase our confidence level. Let's suppose we choose to use a 99% confidence level. Look what that does to the margin of error. It went from originally 0.6 up to 0.8, so we have a much bigger margin of error, and that's going to give us a wider confidence interval. Now let's choose an even higher confidence level, 0.9999, so we're at a 99.99% significance level, or confidence level. And look what that does to the margin of error. It went up to 1.2, and we have now a much wider confidence interval. And so what this illustrates is that if we choose a higher confidence level, then we have a larger margin of error and a wider confidence interval. Now this is both good and bad. It's good in the sense that we're more confident that mu is in the interval than if we worked at a lower confidence level. But it's bad in the sense that we have a wider range of values for mu, means that we have a less precise estimate of mu. And so a wider range of values doesn't really give us as much information about mu. We could, for instance, give a confidence interval by saying, well, we think that mu is somewhere between 0 and infinity. Well, that would be a 100% confidence interval because we'd be 100% confident that mu is somewhere between 0 and infinity. But that confidence interval is completely useless. It gives us no information about what mu is. So a wide confidence interval is bad in the sense that it gives us a less precise estimate of mu. So our goal is that we would like a high confidence level so that we're really confident that mu is in the interval, but we'd also want a small margin of error. So a high confidence level and a small margin of error. That's ideally what we want. Okay. Well, let's look at changing now, for instance, the standard deviation of the sample and look at how that affects the margin of error. So here's our original calculations where we had a standard deviation of 19 and a margin of error of 0.6. Now in our next calculations, let's decrease the standard deviation to 10 and look at what that does to the margin of error. That decreases it down to 0.3. So smaller standard deviation gives us a smaller margin of error. Let's decrease the standard deviation even more, down to 5, and that gives us a smaller margin of error still. So now let's increase the margin of error, or the standard deviation, to 40, and look at what that does to the margin of error. We get 1.3, which is over twice as big as the original. And so what this illustrates is that if we have a larger standard deviation, we get a larger margin of error, which is going to correspond to a wider confidence interval, which means a less precise estimate. If we have a smaller standard deviation, we have a smaller margin of error, a narrower confidence interval, which means a more precise estimate. So ideally, we'd want a set of data with a small standard deviation so that we get a more precise estimate. Okay. Well, let's look at changing one other thing, the sample size. So atop here are our original calculations with a sample size of 3539, gives us a margin of error of 0.6. Now let's decrease the sample size. So let's suppose that we surveyed only 500 people, but we got the same sample mean and standard deviation. Look what that does to the margin of error. It increases it to 1.6. So smaller sample size gives us a much larger margin of error. Now let's change the sample size to 2,000. So that's between 500 and 3,500. And look what that does to the margin of error. Gives us something in between 0.6 and 1.6. Now let's increase our sample size to 5,000. So that's much bigger than the original sample size. Look at what that does to the margin of error. It decreases it to 0.5. So the point here is that if we have a smaller sample size, we have a larger margin of error, means a wider confidence interval, and a less precise estimate. If we have a large sample size, that gives us a smaller margin of error, a narrower confidence interval, and a more precise estimate. And so we see that the precision of our estimate is affected by a lot of different things. We have the confidence level, we have the sample standard deviation, and we have the sample size. Those things all take into account, or those all affect the margin of error. Well, we can use that information to come up with a formula for calculating the necessary sample size for estimating a population mean. And so if we go back to look at Chapter 6, we see that the margin of error for calculating a confidence interval estimate of mu is given by this formula here. The margin of error is this critical value times the standard deviation divided by the square root of the sample size. And so if we so this right here illustrates the points that we've just been making, that the margin of error is affected by the confidence level. Here the critical value corresponds to the confidence level. The margin of error is also affected by the standard deviation and then by the sample size. And so if we just algebraically rewrite this equation, solve it for n, we get this formula right here. So this gives us a formula for calculating the necessary sample size, where again z is our critical value corresponding to the confidence level. Sigma here is an estimate of the population standard deviation, and E is our desired margin of error. So if we know these three numbers here, we can use those to calculate the necessary sample size. Now, one thing that we want to note here is that the population size just doesn't matter. As long as the population size is large relative to the sample size, then the exact value of the population size just doesn't matter. We often think that if we have a larger population, then we need a larger sample size, but this formula here illustrates that that's not the case. As long as the population is large, its exact size just doesn't matter. It could be 5,000, it could be 10,000, it can be 10 million, 10 trillion, it doesn't matter. All that matters are really the confidence level, the standard deviation, and then the desired margin of error. Now, in order to use this formula to calculate the necessary sample size, we need an estimate of sigma, the population standard deviation. And there's at least a couple of ways that we could find this. One way is to use an estimate from a previous survey. Or number two, we could use knowledge of the circumstances. So maybe we just say, well, based off my previous experiences or knowledge of this circumstance, I think that the standard deviation is whatever. And so we can use that as our estimate. So to illustrate an application of this use of the formula for necessary sample size, let's look at example 8.2 from the textbook. And in this example, we want to estimate the mean birth weight of infants born full term to mothers who are age 19 years and under. Okay? So that's our goal. We want to estimate the population mean birth weight, and our population here is all mothers who are age 19 years and under. So the question is really, how many women age 19 years and younger must be enrolled in the study to ensure that a 95% confidence interval estimate of the mean birth weight has a margin of error not exceeding 100 grams. So we're going to enroll these women. We're going to calculate. So we're going to collect some data. We're going to calculate sample statistics, and then we're going to use those to calculate a confidence interval estimate of mu, the mean birth weight. We want to be a 95% confidence level, and we want a margin of error no bigger than 100. Okay? So stated another way, the question is, what's the value of n, the sample size, so that the margin of error is 100 at the 95% confidence level? Okay? And so to use our formula for the necessary sample size, we need an estimate of sigma, the standard deviation of the weights of all infants born to mothers age 19 years and younger. Now our problem doesn't give us any information, and so what we're going to do is use information from a different population. For infants born full term to mothers age 20 years and older, the standard deviation is 385 grams. So here we've got another population of mothers, not the same population, but in a survey of those mothers we found that the standard deviation was 385 grams. Now exactly how they found that number we won't worry about. We're just going to take that number for granted. And so we're going to take this number 385 as an estimate of sigma that we'll use in our formula for the sample size. And so now we've got all the necessary information. We just need to plug stuff into our formula. So here's our formula for the necessary sample size. The z is our critical z value at the 95% level. It's 1.96. Sigma is 385, as we just saw. The desired margin of error was 100. We square that, we do that arithmetic, and we get about 57. So that means we would need to enroll about 57 women. Now when we calculate sample size, we always round it up, never down. Now let's make an observation here that this says that we need to enroll 57 women at the start of the study, or at least that's what it appears to say. But not every mother will deliver full term. We're only interested in this study in full term babies, and not every mother will deliver full term. And so we've got to take that into account. So in other words, we're going to enroll some people, but not all of them are going to be able to complete the study. In other words, some of them are going to attrition out. So we've got to take that into account. So let's assume that 95% will deliver full term. Now this 95% number has nothing to do with our 95% confidence level. It's just an assumption that we're making about full-term births. We're assuming that 95% will deliver full term. So let's take that into account. So let's let the number n denote the number that we're actually going to enroll in the study. And so n times the percent retained, or the percent that are going to deliver full term, equals the desired sample size. So this simple formula right here takes into account kind of my attrition rate and the actual desired sample size that we just calculated up here. And so what we want to know n, that's the number to enroll. We're assuming that we're going to retain 95%, and according to our formula we have a desired sample size of about 70. And so if we do some simple algebra here to solve this for n, we divide both sides by 0.95. So n is 57 divided by 0.95, and that comes out to be about 60. And so that means we need to enroll at least 60 mothers. If we do at least 60 mothers, then according to our calculations, we're going to have at least 57 that deliver full term, and we're going to have enough to get our desired margin of error. Now, our next example, 8.3, I'm going to deal with a somewhat similar situation where we want to know a sample size, but this example is going to involve proportions as opposed to means. So an investigator wants to estimate the proportion of freshmen at his university who currently smoke cigarettes. So that's the scenario. We want to know something about a population proportion. So the question is, how many freshmen should be involved in the study to ensure that a 95% confidence interval estimate of the proportion of freshmen who smoke is within 0.05 or 5% of the true population proportion? So we're going to collect some data, we're going to calculate a sample proportion, and then we're going to use that to calculate a 95% confidence interval estimate of our population proportion. And we want a margin of error of 0.05. We're working at the 95% confidence level. The question is, what's the sample size? Well, again, note that in this situation we're trying to estimate a population proportion, not a mean. And so the formula that we just used in the previous example doesn't apply. So we need a different formula. Now, we're not going to talk at all about where this formula comes from. The book talks a little bit about it, but this is our formula for estimating the sample size, the necessary sample size when estimating a population proportion. And so here's the formula for the margin of error when calculating a confidence interval of a population proportion. If we solve that for n, we get this formula right here. So n is equal to p, where p is an estimate of the population proportion. Take that times 1 minus p, and we take that times z divided by e, where z is the critical z value corresponding to the desired confidence level, and then e is the desired margin of error, and then we square that. And again, note that in this formula, the population size just doesn't come into play. As long as the population size is large relative to the sample size, the exact value of the population size doesn't matter. Again, stressing the fact that we often think that if we have a bigger population, then we need a bigger sample size, but that's not necessarily the case. All that really matters here in determining the sample size is the desired margin of error, your estimate of the population proportion, and then your critical z value, which really depends on the confidence level. The population size just doesn't matter. So now, in order to use this formula, we need an estimate of the population proportion. And so in order to do that, there are at least 3 ways that we could estimate it. We could use a sample proportion from a previous study. So we could use some information that we already know from a previous study, or maybe from a different population, kind of like what we did in the previous example. We could use knowledge of the circumstances. Maybe we could say, like, well, just based off my observations, I think about 30% of students smoke, or something to that effect. If completely unknown, we're going to use p equals 0.5. Now, why 0.5? Well, because p is somewhere between 0 and 1, and so as an estimate, we'll just take the value right in the middle, 0.5. And that's what we're going to do in this case. We don't have any information given in the problem about a previous study. We don't really give any information about knowledge of the circumstances, so we're just going to use 0.5. Okay, so let's summarize our information in this example and plug stuff into our formula. We want a desired margin of 0.05, and we're working at a confidence level of 95%, so that means our critical z-score is 1.96. Now, we're not given any indication as to the possible value of the population proportion, so we're going to take our estimate p to be 0.05. And so now we need to plug stuff in. Here's p, 1 minus p, z divided by e squared. We do that arithmetic and we get about 384.2. Now, what that means in practical terms is that we need to survey at least 385 students. Now in this example we're not going to take into account any sort of attrition, and that may not be a real issue in this problem because it's not a longitudinal study, it's just a point study. So there we go. That's our answer. We need to survey at least 385 students. Now, the last concept that we want to talk about here is the confidence level. What does that confidence level mean when calculating a confidence interval? What does it mean to be 95% confident in our results? And so to illustrate this, we're going to look back at this scenario. Suppose that in a population of all people, systolic blood pressures have a mean of 125 and a standard deviation of 15. Okay? Now, this is going to be a hypothetical situation, so exactly how we know that mu equals 125 isn't at all relevant. This is a purely hypothetical situation. But we're going to use this situation to illustrate this idea of what a confidence level means. Okay? But we're going to pretend that we don't know the value of mu, and we're going to try to estimate it by taking random samples of 6 people, and for each sample we're going to construct a 95% confidence interval estimate of mu. And we're going to simulate doing this a whole bunch of times and analyze the results. And so if we go to the workbook chapter 8 and the worksheet CI simulation, which stands for confidence interval simulation, this is going to simulate doing this scenario a whole bunch of times. So here in the yellow cells we enter our values of our population parameters. Mu is 125 and sigma is 15. Here we'll enter our confidence level, which is 95%. And then in each one of these rows down here, there's a total of I think about 1,000 rows. We simulate taking samples of 6 people. So here's our first sample. The first person had a blood pressure of 150, the second had a blood pressure of 128, and so on and so forth. So there's our 6 people in that first sample. Here's the mean of that sample. We just added those up, divided by 6. That's what we got, 128. Here's the standard deviation of that sample. And then it calculates the margin of error. And then our confidence interval. There's the lower limit, there's the upper limit. Now, this confidence interval either contains the true value of mu or it doesn't. In this case, the true value is 125. 125 is between 115 and 141. And so that interval does contain the true value of mu. Now, in our second sample, the first person had a blood pressure of 102, the second 107, so on and so forth. Here's the sample mean, standard deviation, the margin of error, and then here's the confidence interval estimate for mu at the 95% confidence level using this data from the second sample. Now, like the first sample, this interval either contains the true value of mu or it doesn't. In this case, this interval does not contain the true value of mu because this upper limit is less than the true value of mu. So this interval does not contain mu, and so we put a 0 there. Now, if you hit the F9 key on your keyboard, it will the simulation will generate a new set of samples, and it's going to do 2,000 different samples. So press the F9 key several times, and what we want to do is look at this number up here. This number is titled the proportion of confidence intervals that contain the true value of mu. And so in this particular scenario that we've shown here, there's a total of 1,000 or 2,000 different samples. 95.5% of them contain the true value of mu. And so what we want to do is compare this number to this number here, the confidence level. And notice here that they're pretty similar. And so now we're going to let you play with this simulation a little bit. And so on your own, change the values of the parameters, meaning change mu, change sigma, change the confidence level. Each time hit F9 the key several times, and each time compare the confidence level to the proportion of confidence intervals that contain the true value of mu. So compare that confidence level to that number in the green cell and just look at what you observe.